As you've decided to come to my talk, probably some of you already know what complex event processing means, but as I'm following different questions on Stack Overflow and the mailing list, I usually see that there's a lot of misunderstanding in that topic. So I've decided to start my presentation with some kind of a definition so that we all were on the same page. But before that, let me just quickly introduce myself. So my name's Dawid Wysakowicz, and I'm working as a data engineer at GetInData. I've recently became an Apache Flink committer, and I'm mostly involved in the development of Flink CEP library. Also, just sorry that if somebody were yesterday on Costa's Cluda's presentation, I will repeat a little bit of what he mentioned in his talk, but I think you will find also something interesting part in the second part of my presentation when I will introduce the low-level details of the library. So please stick with me to the second part. Yeah, but as I've said, I tried to put up some definition of what complex event processing means. And when I tried to prepare such a definition, I started looking into some literature. And the two of the earliest positions that mentioned that term provides, I think, pretty neat list of features that a CEP engine should provide. So there's such positions like event pattern detection, event abstraction, event aggregation, and transformation. What I personally think that Flink CEP library brings to the table is that part, so event pattern detection. Of course, I don't try to claim that that Flink does not come with CEP, that Flink is not a CEP engine and it does not come with that feature. It is all. What I'm trying to say is just that the rest of the list is provided by Flink ecosystem itself. So what I think is that Flink CEP library should be used whenever we want to detect some sequence of events in our stream. So some of you may wonder now, what are the use cases for Flink CEP library? I think it's best to describe on some concrete examples. So I will try to talk about analyzing clickstream or in some online insurance agent. So the use case is we want to buy some insurance for our property, and such a process consists of many different small decisions that should be made in some particular order. So for example, we start with providing some basic property info, then we get an initial offer that we can either alter in some way or just accept it. After accepting the offer, we should of course get to know the real general terms of a contract so that we will be aware of what we agree on, and if it is okay, we should make the payment for that offer. So let's now think how we can leverage Flink CEP library in that use case. Imagine we want to be notified whenever a payment was made for some offer that was accepted, so that we can enable guarantees right away. We can use, the only thing we have to do in Flink CEP library in that use case is that we have to provide a pattern that we want to look in our stream. Such a pattern will consist of two separate individual blocks. So the first one corresponds to an offer accepted event, and the second one to the payment. You may notice that each individual block consists of a section that represents the conditions that an event should match to be included in that one block. Each of those individual blocks are joined using some let's say succession operator, which tells us which in an event stream which events are relevant and which are not. Another thing that we can add is an operator within which specifies a time restriction. It does work a little bit differently than windows in the rest of Flink stack, as it doesn't wait until the end of a window to generate some results. It rather serves as a, let's say, time to live for a pattern, so that a trigger will be generated as soon as an sequence appears, but if it doesn't appear in that period, then it will be discarded. I think it fits perfectly into that theorem that the sooner we get some new data, some new information, the more value we can make out of the decisions based on that new data. Yeah, but let's get back a little bit to the consuming strategy, to the different succession operators, and to show you how they work. Imagine a situation that we want to be notified about whenever an offer is accepted. And in the first use case, we want to be notified about each offer, whether it is altered or not. In this case, we will use the followed by operator, and for example, in that case, this event will be like ignored, and the trigger will be generated anyway. But if we were to interested only in those offers that were not altered, we can use the next operator, which tells us that a sequence is valid only if events strictly follows each other. On the other hand, we have operators like, let's say, they're called not operators, that specifies that we don't want some particular event to be present in our sequence. So, for example, we want to be notified whenever user paid for some offer, but he didn't download the general terms, and of course, he didn't read them. So we can say that we expect an offer was accepted, was not followed by downloading of that general terms, and the payment was made for it. So in a case where the download will occur in a sequence, then the like complex event won't be generated for such a sequence. Of course, there are few more. I think Kostas yesterday mentioned all of them, so you can watch his videos or just read the documentation on that topic. But right now, I want also quickly introduce another cool feature that we introduced in CEP library 1.3. So imagine we don't know beforehand how many events, how many times a particular type of event can occur in our sequence. So for example, we want to gather all changes in our offer, but we don't know beforehand how many of those there will be in our stream. So for that use case, we can use so-called quantifiers that specifies that like one of the block can either, we expect that kind of event will occur 3 times in our sequence, or we can say that it can occur some unbounded number of times, or even it is only an optional block of our pattern. So yes, right now I would like to switch a little bit how does it work inside, so because I think it's like an impressive number of features that we provide in Flink CEP library, but of course we always want to know how it works inside, so that we not stumble across some dock in a dishwasher. So basically, the general idea behind Flink CEP library is the non-deterministic finite automaton, which is in fact a graph where vertices corresponds to a states, which corresponds to individual blocks of a pattern. And those states are connected with edges, which are called transitions. And each transition consists of a condition that should be that an event should met in order to trigger that transition, and the type which like specifies some how do we proceed with that event. There are three types of transitions: ignore, take, and proceed. And to illustrate how do they work, let's have a look on how some example pattern is translated into automaton, and how those transitions in that case will look like. So our example pattern consists of four different individual blocks. I omitted the conditions, but let's assume that an event is accepted when the name of event matches the name of a block. So such a pattern will be translated into such automaton. I won't go into details how the compilation works, because it is a really complex topic, but I will show you how, in this case, processing of some example stream will look like. So the processing is based on so-called computation states. So we always start with like the list of computation states is initialized with the first event of our state graph. So in this case, it is the A state. And for each event, we check transitions of all active states. In this case, when we have event A in our stream, for A state, 2 of the transitions will be triggered. And for transition ignore will be triggered, and transition take will be triggered, and it will generate two new computation states named A and B as the target states of those transitions. The difference between ignore and take is that in case of take, we store the event in a shared buffer. I won't go into details of the shared buffer, but the difference is that in take transition we store the event. So yeah, whenever a second event comes, we check it against all active, like all new computation states. In this case, B and A. And in the case of A computation state, B will trigger only the ignore condition, which will generate a new active computation state. In B case, it will satisfy transitions, conditions of 3 transitions named ignore, take, and proceed. So in case of ignore and take, it's just the same as in previous states. So it will generate new computation states named B and C. The proceed condition is a little bit different, as it never generates a new computation state. It just tells the automaton to check transitions in the target state of that transition. So I know it may be, but let's see. So in this case, this transition is not met by B. So like proceed does nothing in that case, and we will end up with just B and C new computation states. But let's see what will happen if the next event is C. And we try to check it against this B state. So it will satisfy both ignore transition, and after proceed, it also satisfies the condition of the take. So in that state, we will generate a new 2 computation states named D, which is the take, which is generated by proceeding that transition and satisfying that transition. In case of C state, because we also need to check against this state and this state, the event C, so it will satisfy the transition take, which will generate the new computation state. So to complete that example, when an event D occurs and the transition is made, so this transition is made outside of an infinite automaton, a match is considered to be found, and in that case it will generate match ACD, and in that case will generate match ABCD. I know that it's just a quick overview of how the automaton works, but what I wanted to stress out in here is that the non-determinism of the automaton. So as you see, there's still some dangling states that occupy some memory. And it can happen whenever we use operators like one or more times or optional, or followed by any succession operator. But we are not left helpless in that situation, because we can make ourselves secure using, for example, the within operator, which in fact will, after some period of time, free some of our partial matches. Or in case of the one or more operator, we can add a condition until, which based on some properties of event will also stop the processing. Yeah, so that was like for the how it works underneath. And just to end up with some teasers, what I'm personally thrilled about, what will be added into future to Flink CEP library. So one of the most important feature is that we want to support, support in SQL the match recognize clause, which will be translated internally into Flink CEP native library expressions. And the other one is that we want to support dynamically ingested patterns, so that it will be possible to provide a separate data stream with patterns that will be dynamically added to a stream and matched against it. So for example, it will be possible to build some UI, some rules engine that will allow users, technical users, to provide patterns. Yeah, so just to briefly summarize it, what I really want to stress is that Flink CEP library is, in my opinion, generally should be used for pattern detection, and with all the cool stuff of the rest of Flink stuff, it provides the CEP engine, and there's few new features that will be really cool in the library, and of course there's also a lot other way to improve it, and we're very welcome to hear some use cases, some ideas from you. So yeah, that was pretty much everything from my side. Yeah.
Are there any questions?
As you encourage us to give idea here, so have anybody think of adding an operator to push down any state to a stack structure, like to make to give me the power to make that automaton push down automaton? Like I would, after matching some type of events, then I would save the state, not the Flink state, but any arbitrary variable I want, like counting how many events I have already seen. I would push down that during the matching, then maybe matching other events, then I would pop out that state, and then I can compare, for example, the values.
Yeah, so
that would basically extend the automaton to push down automaton, I think.
So yeah, so I think you're like you would like to have a control in the user space of the automaton, like to expose the functionality of automaton to users.
Well, basically not modify the automaton or something like that, like just to bring the stack structure to the user, to not use the non-deterministic finite automaton, but to use the push-down automaton.
Yeah, I think it's very sophisticated structure and very fragile. So I don't think that it would be like really possible.
I don't know if it is possible. Just like parsing a programming language basically needs this. So all the parsers around use this idea of saving the the predicates you match during the matching to the state and then popping them out. Like you have to match opening curly brace, then you have to match the closing one, and so on. So the idea and the implementations are out there. I don't know how to adapt them to streaming, but maybe.
Yeah, I will have to like think about it for a while. Yeah, but it's a nice idea. Yeah.
All right. Unfortunately, we ran out of time. So let's thank again our speaker, Dawid Wysakowicz from GetInData.
Thank you.